Hello, my friends. Today I am happy to have a great opportunity to chat with you. I invite you to join me in the precision grinding of a 1000 millimeter long precision cast iron straight edge. My friend gave it to me specifically for another test grinding session. This particular job turned out to have some unexpected twists, so it definitely deserves its own video. After grinding, I will perform control measurements of the finished working surface using an optical instrument designed specifically for ultra-precise inspection of reference straight edges, the laboratory device OL 1600. I assure you, with a careful measurement procedure, this instrument achieves accuracy within 1 micron. That's about 40 millionths of an inch over the entire length, which fully corresponds to its passport specifications. All measurements are tied to the optical axis of the OL 1600, making them perfectly accurate in terms of straightness. A photon in space travels in an absolutely straight line, and that is what provides the flawless optical axis of the instrument, the zero coordinate reference at every control point. So, together, we will renew this precision cast iron straight edge and then verify the quality of the newly created working surface to find out exactly which accuracy class it has achieved. For new viewers, it's worth noting that this old surface grinder was recently restored by me. I hand scraped the x-axis ways, and now the machine is capable of grinding surfaces very accurately, even the working surfaces of precision inspection tools. I invite you to see that for yourselves in my previous videos. The restoration was extremely thorough, and today's job is only possible because the machine can now maintain very high accuracy, thanks to perfectly straight ways. I've uploaded a whole series of videos about that restoration. Everything is shown in detail, step by step. I gained a lot of interesting experience during that project. Many completely unforeseen issues kept appearing. The geometry of the vase was checked with an autocollimator, which guaranteed high accuracy. I highly recommend watching that series. Almost everyone will find something new and useful there. All the scraping was done entirely by hand, and the initial error was half a millimeter. Still, little by little, I removed everything that needed to be removed, and the vase became straight. But don't think I'm only going to talk about this machine and grinding straight edges. My interests are much broader. This is just the current stage of development of my workshop. Soon, I hope, we'll move on to new topics. Right now, I've taken the magnetic chuck off the table, and now I need to prepare the table surface for work with a special tool, a precision ground ceramic lapping block. There's a video about it on my channel, and other creators have similar material too. It's an incredibly useful tool. I can't imagine working without it. Very often, it's simply irreplaceable. It's not only for removing accidental edge burrs or cold work craters. It lets you feel the condition of the surface, by touch, by sound, by the sheen. Check flatness and make sure there is no bumpiness whatsoever. With the same lapping block, I'm now cleaning the rust layer from the working surface of the precision cast iron straight edge. This is still the original factory-made working surface. I'm doing this not only to see the current condition. First of all, I need to set the straight edge on this very surface and grind the support feet. So the surface needs at least a light cleaning. With coolant, the rust comes off nicely, without clogging the pores of the block, and very soon the surface is ready. And now we can see the surface revealed by the lapping block, and it already tells us something. The surface is not worn. The crosshatch network of dust removal grooves is almost perfectly uniform across the whole area. This straight edge is probably 40 to 50 years old, but it looks like it was hardly ever used, though it did manage to pick up some rust. The rust is evenly distributed and not deep at all, so it causes no problems. Now I can safely use this face as the reference for grinding the support feet. I raise the spindle. I need to align the plane of the straight edge perfectly with the table plane, and then carefully, without distorting the body, clamp it to the table. Sometimes it is worth using a few drops of epoxy glue to avoid any deformation during clamping. Here, for example, you can see a workpiece glued at 8 points, 8 tiny drops of epoxy. The part is fixed to the table with almost zero distortion. This one has already been torn off and flipped. Now the freshly ground opposite side has become the reference. And don't worry about the few percent shrinkage of the epoxy. The linear effect is negligible. I simply located the points of full contact between the straight edge and the table and placed the clamps exactly there, avoiding any noticeable distortion. When I grind straight edges that are more flexible than this precision cast iron straight edge, I always use drops of epoxy glue that fill any gaps before clamping, or even attach the straight edge only with glue, without clamps at all. Of course, grinding very carefully in that case. So right now I am going to grind the two support feet. This is the mandatory first step. The grinding wheel is quite wide. It covers the entire width of the straight edge in one pass, actually even wider than the straight edge itself. Therefore, I only need one series of straight passes, lowering the wheel along the z-axis until both feet are fully cleaned. You have just seen one of those passes. In total, I needed about 10 passes. Of course, now both support feet lie in one common plane that is parallel to the working surface of the straight edge. I check the condition of the surface again with the lapping block. It reveals submicron irregularities and slightly levels the surface at the same time. This way I can see the actual quality of the plane. It's not mandatory, but it's definitely helpful. Don't expect to see a mirror finish here. The height differences are less than 1 micron, yet they are clearly visible. I can say that confidently because it's very easy to confirm with a dial indicator, comparator, with 1 micron, half micron, or even 1/10 micron sensitivity. I've done it and shown it many times in previous videos. One division on the comparator scale equals 1 micron, and that lets me see exactly how wavy the surface is and within what limits the peaks and valleys lie. So the straight edge is now standing on its freshly ground feet, carefully clamped to the table, and I'm starting to grind the working surface itself. It's extremely important to find the very first touch of the wheel, lowering it along the z-axis very slowly, with minimal depth of cut. This requires patience. I just saw the first tiny sparks and immediately stopped lowering the wheel. They were very faint and probably not visible in the shot. After that first contact, I probably removed about 3 microns, maybe 2, maybe 5. It's cast iron, it sparks less, and only the very tops of the textured surface are being cut. I lower the wheel another 10 microns, 2 divisions on the hand wheel, and make the first full pass. I stop the machine. Sparks were consistent along the entire length, meaning the wheel engagement is approximately the same across the whole surface. It's interesting to see what the surface looks like after removing roughly 10 to 15 microns from what was a rusty face just minutes ago. In my opinion, this is the most fascinating part of this video. You can clearly see how the old rusty geometry of the original working surface has perfectly integrated into the new, almost perfectly flat one we've just created. Right now, we are looking at both surfaces integrated together. Unfortunately, I didn't expect the original surface of this old precision cast iron straight edge to be so incredibly flat already. The very first proper pass covered the entire face, so I didn't set up an additional dial indicator for precise Z-axis feed monitoring, which is easy to do when needed. If I get another similar precision cast iron straight edge, I'll do exactly that. I'll remove just 1 or 2 microns per pass and film the surface after every single pass. It will be like real three-dimensional layer-by-layer scanning with precisely known depth removed each time. I'm almost certain that opportunity will come sooner or later. For now, you can just watch how it's possible to control their feed by watching the indicator. Come on, agree with me, this is amazing. Just one pass, only 10 to 15 microns removed. This straight edge is approximately 40 to 50 years old. No significant surface deformations have occurred during all this time. Look how beautiful its working surface appears at this moment. The oxide patina has perfectly created contrast between the machined portion and the unmachined one. An almost uniform pattern has emerged from the recessed dust collection grooves. Examining the surface, we can clearly see where the high spots and low spots were, and we roughly understand their position relative to the correct plane before this grinding. I could not have invented such an epic scene myself. It happened completely by accident. But this is an important observation. It is absolutely accurate and very convincingly shows us the exceptionally high stability of cast iron. At least this particular cast iron straight edge has retained the condition of its working plane over approximately half a century, possibly absolutely unchanged, or maybe plus minus 10 or 20 microns. I don't even want to grind it any further and ruin this beauty, but I'll still grind a few more hundredths. But before that, I thoroughly cool the surface to eliminate thermal deformation. For this, I switch the coolant supply to flow through the hose and cool the straight edge surface for some time. Although coolant is constantly flowing to the cutting zone during grinding, the metal still warms up a bit anyway. The mechanical impact of cutting is simply too strong. That's why I need to cool it additionally now. Otherwise, later a sag will appear in the middle due to thermal deformation. I bring the grinding wheel into working position. Lower it by 5 microns. That's one division on the hand wheel. I make another pass. Five microns, cast iron material. Not many sparks. I'm already finishing the grinding, just a few more passes. I make the passes in only one direction, from right to left. It's also possible the other way. The main thing is to choose one vector, at least on this particular machine, according to data that are not yet fully verified. This method slightly improves the grinding quality. At the end of each pass, I move the grinding wheel out of the working area by feeding in the Y direction and return the table to the starting position. I feed the grinding wheel back into working position. Using Y, lower it another 5 microns and perform the next pass. I'm satisfied with how the grinding is going. The wheel removes a few microns, the spark is small but, most importantly, stable in intensity across the entire surface. This tells us the result should be very good. A few such passes with minimal depth of cut, with surface cooling between them, and the grinding is finished. I deliberately left the shallow traces of the old crosshatch grid on the surface. I like that it's there, and besides, it gives this straightedge individual character. I expect that I now have a high accuracy class for this inspection straightedge, and I believe it is made from the best possible blank, an old, roughly 40-year-old inspection straightedge, which significantly improves its quality in terms of long-term stability. After grinding, I again lap the surface lightly with the ceramic lapping block. Please note, removing even 1 micron with this particular block that I'm using right now is extremely difficult. It's unlikely anyone could do it in an hour of hard work. It will only gently knock down the sharp micro peaks on the surface, thereby improving it. But now this part still has to undergo proper testing. Right here and now I can perform the first quick approximate surface tests. I have detached the precision cast iron straightedge from the table so that it is no longer influenced by the table at all. The last time I showed the grinding of a similar 1 meter precision cast iron straightedge, I carried out measurements without detaching it from the table, directly on the machine, and I did it that way because back then I was checking not the straightedge itself, but the performance of the machine along the x-axis. Today my attention is completely focused on the precision cast iron straightedge itself, so it must be in a free state. No influence from the clamps should remain. I placed a stand with a 1 micron sensitivity comparator on it. Watch the comparator needle. One division on the scale equals 1 micron, from 0 to 10. That's 1/100th of a millimeter. This test already gives some information about the flatness of the surface. It's a very good result. Only a few microns of variation, both lengthwise and crosswise. The crosswise readings are direct. What the comparator shows is exactly what we have. Because the support platform doesn't slide, it only rotates. Lengthwise readings often need to be multiplied by 2, because the base platform itself moves along the surface. This stand with comparator has a support plane diameter of 130 millimeters, 5 and 1/8 inches, and the comparator overhang is also 130 millimeters, 5 and 1/8 inches. The total length from the comparator probe tip to the end of the support is 260 millimeters, 10¼ inches. Functionally, it is absolutely identical to a repeat ohmmeter, very convenient for quick testing. The second possible test is interaction with a reference flat surface. It should behave exactly like this. The center of rotation should be here. Identical result from the other side as well. But my phone distracted me, and unfortunately, I forgot to film this episode to the end. But these are only express tests. In my workshop, I have the instrument for real testing, the OL1600. I have already talked about it in previous videos. I built a dedicated stand for the OL1600. And now I can adjust the height position of the instrument, which allows me to test not only regular inspection straight edges, 50 or say 70 millimeters high, 2 or 2¾ inches, but also much taller inspection gauges. So, the freshly ground precision cast iron straight edge is now installed on the stand for the OL1600. The key elements of this stand are the height adjustment units for the standard jacks of the OL1600. These jacks provide fine adjustment of the instrument position. Coarse adjustment is done with the earlier mentioned T-slot units based on USP12 blocks. The entire system is securely fixed to the wall to save space and to ensure reliable positioning of both the OL1600 measuring instrument and the precision cast iron straight edge being measured. I will probably make the next video about installing reliable heavy-duty wall anchors, because this is something many people may need. And I have been using this method successfully for several decades. It is absolutely simple, fully proven, and often very useful. I have seen similar glue-in anchors for sale, but this version is a bit different, more universal and significantly cheaper. The stand is fully functional and reliable, but its base is an old and somewhat rusty I-beam. I understand that ideally all parts should receive proper decorative coating, but that requires time and resources. And as you know, there's never enough time, and resources are also limited right now. So I have to keep ignoring the decorative side of things, because there are much more important tasks for me, and I need to focus on those. Therefore, I sincerely ask you to forgive the already traditional lack of proper exterior finish on the tools I built. They certainly deserve better. But still, they are original, rational, and they perform their function perfectly. Moreover, I have a forced opportunity to emphasize once again. The primary things are the idea and the function, conformity and reliability. External appearance is desirable, but not mandatory for one-off experimental items. Let's return to the measurement process. I decided that 8 control points are sufficient, with a step of 112 millimeters, 4 and 3/8 inches, between them. Already in the previous video, with the OL1600 optical instrument, it turned out that from the recorded video footage on the monitor, I can read the instrument values more accurately than directly on the small screen of the device itself. This is because I have to film the episode quite dynamically for you, and I simply don't have time to examine the readings too carefully. Otherwise, an already slow video would become completely unbearable, and of course I want you to actually watch it. At the same time, filming dynamically does not reduce the accuracy of measurements or reliability at all. The accuracy simply comes later from analyzing the recorded material. Because when working with the video, I have every opportunity to process the data properly. And of course, that's exactly what I do. I will use the same approach now. So all we have left to do is carry out the measurements, and we will know the result. I film the entire measurement sequence without stopping the camera from beginning to end, as quickly as possible, for obvious authenticity of both the process and the results. I turn on the instrument and begin. I will review the instrument readings later in enlarged format on the monitor, determine the exact values, and display them on screen. And you will see these final values right now. I will add them as numbers next to the small screen. First control point, look at the screen. The height reading here is 0. Of course it should be. Before filming, I adjusted the position of the OL 1600 relative to the measured plane. I move the carriage to the second control point. Second point, 1 micron lower. I move to the third point. Third point, again the same reading, 1 micron down. This drop is relative to the optical axis of the instrument, meaning the second and third control points are at the same height relative to the optical axis, neither drop nor rise between them. I move to the fourth point, same thing, 1 micron lower, same position. I move to the fifth point. Here it is 1 micron higher, reading 0. Sixth point also 0. 7th point, 1.5 microns lower. The whole time I haven't touched the scale, it stayed at the zero division. All previous point data I added only based on video image analysis, looking at almost imperceptible deviations of the reference line. But the 8th point was clearly 1.5 microns above the optical axis. That was already visible, so here I decided to make a correction by adjusting the scale with the hand wheel. I added 3 microns, and assuming that would probably be enough to determine the exact values from the video, I finished recording this measurement. Later, studying this video recording, I analyzed the images and concluded that at control point number 8, before adjusting the hand wheel, there was a gap in segment A1 between the line and the scale, left side of the screen, while at point B1 there was no gap at all. That's what made me turn the hand wheel. After moving the hand wheel exactly 3 microns, image shown on the right, the picture reversed. At point A2 the gap disappeared, and at point B2 a gap appeared. That was exactly the same as the one that had been at A1 before the 3 micron adjustment. From this I understand that if I had turned the hand wheel only 1.5 microns, the gaps at A2 and B2 would have become identical, which now, after analyzing the images, tells me that the real reading at point 7 is minus 1.5 microns, and at position 8 it is plus 1.5 microns. So here are the obtained data about the surface condition. I made this single compilation of all the screen images at each control point. We can see that after grinding, the error across the entire 1000 mm length, 39 and 3/8 inches, is within 3 microns, from measurement point 1 and from point 8 to the very ends of the precision cast iron straight edge. The surface is highly unlikely to drop or rise significantly. So I consider these results valid, even though the instrument carriage doesn't reach all the way to the extreme edges of the measured surface. Here are the finally processed measurement results, with the zero level tied to the 2 highest points on the surface. With just a little effort, some experience, and the right lapping tool, I can easily reduce the surface error from 3 microns to 2.5 or even to 2 microns and achieve the highest flatness grade. The old Soviet class 00, according to GOST standards, up to 2.5 microns, tolerance over 1000 millimeters, 39 and 3/8 inches. But even without this additional hand finishing, this precision cast iron straight edge already meets grade 0. That is 2 full steps higher in accuracy than the widely used standard workshop grade for precision cast iron straight edges, which is grade 1, where the flatness error does not exceed 10 microns over the total length of 1000 millimeters. 1 step higher still is grade 01, where the error is limited to 6 microns. In the Western world, the requirements of the standards are identical, but the grade names are different. I don't know them exactly. Whoever knows, please write in the comments. I would be very grateful. So we can see that the result of this work is more than decent. That's the whole story of bringing this 1000 millimeter precision cast iron straight edge back to life. Recently I started a new big project, the full restoration of another structurally identical surface grinder, an LSH5. This second machine is no longer rented. I bought it outright, so now it's truly mine. That means I can and must do a proper, no compromise, from A to Z overhaul using all the experience I've gained. Investing time and money into my own machine finally makes perfect sense. It's going to be a very exciting project. But right now, my YouTube channel hasn't yet reached the level where it can fully support itself. And I need to keep working actively. So, at the moment, I completely depend on my sponsors and patrons. If any of you feel the desire, and of course the possibility, to support the channel and this new grinder project, I would be incredibly grateful. A huge thank you to everyone who is already supporting me. Only because of you, I'm able to keep working and creating new videos even in these difficult wartime conditions. For the new machine, I still have to build a proper workshop building, a heavy overhead crane, and a serious foundation. All of that costs a lot of money. I won't be able to manage this without your help. If someone would like to buy a similar precision cast iron straight edge, an autocollimator, or an OL 1600 from me, I still have a few pieces in stock. Please write to me by email. You'll get a beautiful, proven, freshly calibrated, laboratory-grade instrument, and you'll help me tremendously to speed up the LH5 project. Thank you so much for your support, for watching, for every like and every comment. See you very soon. Goodbye.